We'll get started on the next topic on corrosion and stray currents. What I'll be talking about is corrosion and reinforcement, different types, corrosion rates. Corrosion is a lot of different things. I'll then deal with the corrosion monitoring. You raised a question on how to verify the surface life. Let's dealing with that. Stray current corrosion and conclusion. We talked about deterioration of concrete very briefly. We have a lot of ambitions when doing designs and selecting materials, but the real quality of our structure is not determined before it's executed and cured. I think we all know that the best intentions don't necessarily lead to a good result if things inside are different. All of what takes place in the early ages of construction phases have a high influence on the transport mechanisms. We normally talk about deterioration in relation to concrete and in relation to reinforcement corrosion. And this is the one that we'll be dealing with in this presentation. Reinforcement corrosion and corrosion as such requires, in most cases, both oxygen and water. But not always. We can have corrosion under some circumstances where oxygen is not required for the corrosion process to take place. This is very important to know this. That deals with when we are talking about stray current, and it deals with when we're talking about bimetallic corrosion, galvanic corrosion, coupling two different types of metal. In that latter case, it's a question of potential differences, either across a concrete member or between two different steel components. Normally pH has a very high, normally concrete has a very high pH value. If we have fly ash and silica fume, it might be down to 10 or 10.5 in pH value. So that actually it lowers the resistance towards corrosion to some extent. But the very high pH value makes it electrochemically unable to corrode because a passive film is formed on the reinforcement layer. That passive film can be deteriorated either if the concrete carbonates, meaning carbon dioxide from the atmosphere, enters, or if we have chlorides in a critical amount that reaches the reinforcement layer. And also if we have stray currents and bimetallic corrosion. Even in those two cases, that passive film or the resistance towards the corrosion has to be overcome. Normally, if we look at a volume unit of iron, if we have a lot of oxygen, we'll have a big volume increase, and it will be a brown corrosion rust. This is the one we all know when we think about corrosion. If we, however, have chlorides in a high amount, or if we have underwater corrosion, we can have very limited volume expansion of our steel member, and that may not lead to visible signs of corrosion. You can see that it's black, white, black, and brown in color, and some of them are also intermediate stages in green rust, and that's a complex which is formed with chlorides in the concrete that makes it green. This reinforcement bar, making an excavation looking at the reinforcement, you can then see it actually change in color as oxygen accesses it. So you start off seeing a black steel, and it will then turn into green and white, and if you wait long enough, brown. We know when we have oxygen enough, it will cause concrete to crack. And sometimes we can even see if it was as on the as-built drawings, the reinforcement that is. Normally we say that when we go below water level, we don't have any corrosion because oxygen is very limited in those cases. This is an example where we're 5 to 6 meters below is the Swedish bridge. 5 to 6 meters below water, we found very severe corrosion, as you can see here. They had found a lot of corrosion, and they had built cofferdams around these concrete piers. I went in my young days to do potential mapping on these, and then found this, where you had no visual signs on the concrete surface. This is a case where we have what is called macrocell corrosion. This means that you can have a corrosion process run over very long distances. Not because you have oxygen below that, but because you have very low resistance. You remember Ohm's law. You have a voltage difference. We have that below water and above water. And then it's possible for a current to run if the resistance is low enough. So this is a case of that. We know from many of our existing structures that we actually have corrosion underwater. What we don't know in detail is what is the water-cement ratio on the concrete and the chloride ingress parameters, but we can avoid these. But normally on new structures, we know with very low water-cement ratios, we don't expect this. Again, normally we have cracking in parallel to our reinforcement, but sometimes if you have a crack or a localized attack, you can also have reinforcement just completely disappearing in one location without visual signs of corrosion. There's a lot of information on this slide, and I don't expect you to take all of that in. What you need to know is that where we have iron that goes into solution, this being the reinforcement, this being the concrete, we have chlorides entering the concrete in a critical amount down here. Passive film is destroyed. Iron would go into solution, and the motor of the process for the corrosion process is a reduction of water and oxygen in the vicinity of the area. That causes a corrosion cell to form and a corrosion current to run in this area. So this is the area where we have the corrosion, and these areas out here, they don't corrode. And we have different cathodic reactions depending on which environment we have. You saw this also that Carola showed you, so we have a resistance towards deterioration in the outer surfaces of the concrete before we have the onset of corrosion. We have a lot of, these are some premature deterioration of Nordic marine structures, and we have a lot of, we talked about that, a lot of surface life requirement. An interesting thing on, for instance, on the Messina Bridge is also there's a volcano just next to it. So maybe some material could be used for the construction. That was one thought. But the other one is that when the volcano erupts, you have a very high concentration of carbon dioxide. So maybe it could cause it. If it's 200 years you're looking upon, it may could cause carbonation of your concrete. The challenges when we look at operation and maintenance, that is that you can have hidden degradation, as you don't always have visual signs of deterioration. And basically it could lead to unknown structural safety. If you want to do preventive maintenance, you have to know beforehand that you should apply this preventive maintenance. And the challenge is very often when you do visual inspections, a lot of the management systems, that's a visual inspection until you have a visual sign of degradation, and then you start your repair process. But you don't normally look below where it's submerged in the soil and so on. Carbonation, as I said, carbon dioxide reacting with calcium hydroxide of the concrete, that reduces the pH level, and if that reduction in pH level is reaching the level of the reinforcement, it can cause it to corrode. Chloride-induced corrosion, that's a more pitting type of corrosion, localized attack. The sources are de-icing salts and marine environments. Hardening accelerators was used in Europe until the mid-70s, and we still see now and again a case where they have been used as hardening accelerators and where you have a very aggressive corrosion. That's calcium chlorides that were used in those days. It would namely be on precast concrete members because they wanted to strip the formwork and have a production running. Chloride ions, they can go in and break down this passive layer, and then you can have the iron going into solution. But at the same time, it acts as an acid attack. You're lowering your pH level around the reinforcement in that case, which is also the reason why you have a more accelerated and a more higher corrosion rate. It is only the chloride ions that are into solution in the pore solution that can cause corrosion, not those that are bound chemically or physically. Critical chloride concentration, this is a rule of thumb and it's quite a large range. The lower the higher our porosity, the lower threshold level is, and vice versa. With a very high durable concrete, the chloride concentration is higher. It has a high impact, what is a water binder ratio, different cement types bind chloride in different amounts. pH value is of importance, the pore system, humidity, temperature and homogeneity. If we then look at microbiological corrosion, this is not so much with reinforced concrete, it's with steel in seawater and in soils. If we have sulfates present, anaerobic condition, meaning no oxygen in the environment, sulfate-producing bacteria and organic material, we can have microbiological corrosion. You have examples here. This is a steel casing where the steel was corroded in 8 millimeters over 15 years. So this is a very aggressive corrosion type. Different corrosion rates. Carbonation, we don't normally worry about carbonation because, first of all, the corrosion rate is so small when it gets to the depth of reinforcement. Secondly, for a lot of our marine structures, inland structures, if you have fairly good quality, you don't have a problem with carbonation. Chlorides, they can be quite aggressive, up to 0.5 millimeter a year. Sulfate-producing bacteria, they have had reported corrosion rates of up to 1 millimeter a year. Stray currents, they are a real challenge in this respect because corrosion rates in relation to stray currents is directly proportional to the current that you have from the outer source. Iron would go into solution at a rate of 9.8 kilos per amp per year. So, to which extent you have a corrosion rate on your reinforcement highly depends on the current that you have and the length where your reinforcement is affected by the stray currents. We can be glad that we did not choose to have lead as a reinforcement material, because as you can see, it will be much worse in that case. Galvanic corrosion, that depends on which materials we are talking about, which environment we are talking about. When we have what we would call a traditional repair, way of making a repair, as you saw before on the anode and cathode, this is the place where iron goes into solution and where we have an active corrosion. And these areas around it is the places where we have oxygen reduction. You can also see that there is here a potential difference, so we have a more positive potential, and where we have the anode, the potential will be more negative, and so on the other side of it. If we then choose, just from visual inspections, excavating this area and make a very good repair in this zone, we will be certain that this area will be a cathode. It's in sound concrete. But if we have around here, we still have chlorides, for instance, in a critical amount that did not cause corrosion here because we had a higher amount around where the corroding part was. Now all of a sudden they could cause corrosion in this area. And we have a very good cathode in many cases to support this reaction. This is an example, a school example on how that can look. This is one of our Danish marine bridges that was built in the very early 60s. Shortly after, we had extensive deterioration due to corrosion. And you can see the extent in repair that was done based on a visual inspection and where the delaminations were. Doing a special investigation of these parts, we found corrosion in so many of those, just in the circumference of those, many of those repair zones. supporting this